Welcome everyone to the series on molecular dynamics. As a continuation to the last week's seminar, so this week Rajas will cover the steps continuation from the instructions for the participants. Kindly please keep your mic as well as your video off so that there won't be any disturbances. And make sure you type your questions in the chat boxes as well as use the send option from where we can try to answer the question spontaneously or we'll take at the end of the session as per the speaker's convenience. Also, those who are viewing from YouTube can use your comment ask questions in the comment sections. So now Rajas will take this session.
Okay, thank you. Welcome everyone again to the second part of the presentation of preparation steps on the for a molecular dynamics simulation. So I'll briefly summarize what did we do in the previous presentation. So we'll briefly revisit what are the steps involved in a molecular dynamics simulation. So in the last presentation, we prepared the system. That is, we got the PDB file of the protein on which we wanted to do the simulation on. Then we solvated the system. That is, we put water ions around the protein, and we also put water as well as ions around the protein. And then we performed energy minimization to remove all the steric clashes. So today we will be performing the last two steps, which is the equilibration of the system and the production simulation. So once we are done with the energy minimization, it's always a good idea to visualize your energy minimized structure once before proceeding, just to make sure that there's nothing abnormal in your system before you proceed ahead towards the next steps. So I'm just opening it with VMD program just to visualize the structure once. So here's the structure. It looks pretty normal. So, but there can be sometimes it can also happen that when you visualize the protein using VMD or PyMol, it looks normal, but when you do the equilibration, it might give you some problems. That can also happen, but regardless, it's always a good thing to visualize the protein once and check that there's nothing really abnormal with the protein. So once you have done that, we'll just close this and we'll get back to the terminal. So I'll explain you what happens during the equilibration. I'll give you a theoretical aspect about it. So we do the equilibration before doing the actual simulation, so that all the non-protein particles that are present around the protein, which is in this case it's water and ions, they are brought to the same thermodynamic state as protein. So that's the main objective of why we do the equilibration. So to do that, how do we achieve this goal? So for that, we impose something called as position restraints on the protein. So what does that mean? That means on all the heavy atoms of the protein. So when I say heavy atoms, I mean all the carbon, oxygen, nitrogen, and perhaps sulfur here and there. On all these atoms of the protein, not hydrogens. So that's why I'm saying heavy atoms. So on all these heavy atoms of the protein, we will apply an energy penalty. So that energy penalty will be certain value, that is certain amount of kilojoules per mole. So when the protein gets displaced too much from its initial position beyond a certain permitted value, and this energy penalty is imposed. So this essentially prevents the protein to move too much further, to displace too much further from its initial position. So this is why it's called as position restraint. So it's almost like in some movies they'll show how they kidnap a person. They'll put rope around the hands of the person. They'll tie the uh, hands and legs of the person with a chair or so on. Position restraint is something like this. So it's not exactly completely preventing the motion of the protein, but it's more like restricting the motion of the protein so that the protein does not displace too much from its initial position. So in the equilibration, we'll be doing the equilibration in two phases. One is called the Nbt phase and second is called Npt phase. So we'll be starting with the Nbt phase. And what happens in the Nbt phase is the Nbt is a short form for constant number of particles, volume, and temperature. So what happens in Nbt? What that means is that we'll make sure that volume will be the same, uh, but the pressure will be fluctuated in such a way that the pressure of the system will be fluctuated in such a way that temperature is stabilized. So if you studied basic thermodynamics during your plus two or PUC, there's something called as ideal gas law, which is shown in the equation here. PV equals nRT. So which means where P is pressure, V is volume, N is number of particles in your system, R is a constant, it's something called as ideal gas constant. It's a particular number, and T is the temperature. So if we apply this law into our molecular dynamics system, we'll be fluctuating pressure. So let's say the pressure will be increased or decreased to a small extent. In that case, the number of particles is same, volume is also same. The temperature is also, uh, because the number of particles and volume are same, when we fluctuate the pressure slightly, the temperature will also accordingly fluctuate. That means if we increase the pressure, temperature will increase, and in the same way, if we decrease the pressure, temperature will also decrease. But the main goal is that the temperature of the uh, non-protein particles, that is water and ions, matches to that of temperature we would like to we would like to have on the simulation, which is around somewhere around the room temperature. So this is the Nbt phase of the equilibration. In Npt phase, it's the same thing, except even the pressure also will be maintained constant. So because the pressure will be maintained constant, temperature will also be maintained constant. So we'll open the to do this, first we'll be doing the Nvt equilibration step. To do the Nvt equilibration step, we'll do this command. Oh, sorry. We'll do this command. So the first command, which is gmx growmpp dash f nvt.mdp file dash p is topology file dash c is a grow coordinate file, which is the energy minimized grow coordinate file. R is the restraint file, that is the starting reference file based on which GrowMax will check and impose the restraints. Output is nvt.tpr. So for getting the MDP file, you can get this file from the website, from the link I have provided in the presentation. You can get this file from the link. So we'll just check what's inside this MDP file. So you can see that there are many parameters here. I'll just explain you the most important parameters. Title means it's the title of the parameter file. define depose res. That means when you say define dash depose res in the parameter file, that means you are giving instruction to the GROMACS telling that impose position restraint. So when you say that, GROMACS will refer to the topology file which you are giving. So in the topology file, if we go back to the topology file, if we go back and check to the topology file, we'll go to the end of the topology file. So here's a paragraph in the topology file. Hashtag if def posres, then next line hashtag include posres position restraint dot itp, hashtag ndef. So here it says if the parameter file is giving instruction for imposing position restraint, then it will include it will take the reference definitions for position restraint from this file called posre.itp. So that's what instructions for, that's what's written in the topology file, which is the instruction from where the GROMACS will impose position restraint. So it's saying impose position restraint from posre.itp. So we'll check this file, posre.itp. So you can see that here there are list of different column of numbers and with the different values. So this goes on to the end of the system. So the first column is the atom number. So every atom you see here is a heavy atom. It will be either carbon, oxygen or nitrogen atom, atom 1, atom 5, atom 7 and so on. Here then fx, the column fx means the amount of position restraint. That is the, when I told you, remember I told energy penalty, this is the exact energy penalty that GROMACS will apply in the x direction. So it's 1000 kilojoules per mole per nanometer. That means if atom 1 deviates by 1 nanometer in the x direction, the GROMACS will impose energy penalty of 1000 kilojoules per mole on this particular atom. In the same way, for Fy it is also 1000 and for Fz it's the 1000. So it's the same thing except Fy means it's in the y direction, Fz means if it's in the z direction. So this is where this is how GROMACS imposes position restraint. You can see that it's present for all the heavy atoms. It goes all the way till the length of the protein. So it goes till the 1960th atom. And this is how position restraints are imposed on the system, on the protein during the equilibration step. So we'll go back to the parameter file, that is the Nbt file. So when we say define posres, that means we are giving instruction to GROMACS to impose position restraint. Then there's something called as integrator. So here we are saying integrator equals MD. That means it's a method how GROMACS integrates the laws of Newton's equations of motion. So if you remember the first presentation I presented, where the first step of MD is calculating the changes in the imposing velocity of on the particles and calculating changes in position, and then integrating it back to get new set of positions. So this is a method called as leapfrog integrator. I won't go too deep into this. It's a much more advanced topic. It's not compulsory to know to do MD simulation. I'll just say that it's a method by which GROMACS uses to integrate the Newton's equations of motions. So the next step is number of steps. So that is how many steps of equilibration we should do. So actually, we are supposed to do almost 50,000 steps, but I'm using just a personal computer. That is, I'm just using a laptop to demonstrate this. So I don't have the computational power, and it takes really long time to do that. So for that, we'll only do 500 steps, and dt is the time step for time taken for each step. That is the time period for each step. So here it's the unit is in picoseconds. So it's 0.000, sorry, 0.002 picosecond. So that means the equilibration, if we calculate how long the equilibration will be, so it will be 0.002 into 500, which will be 1 picosecond. So here we'll be doing 1 picosecond equilibration, but actually we need to do minimum this much, that is minimum 100 picoseconds of equilibration. But because my computer is not very powerful computer, just for the sake of this presentation, uh, just for the sake of time, we are doing just 500 steps. This is the most important. These are the most important parameters. The other parameters are next output control. That is for how many steps the coordinate should be saved. Here it says 500, so I can change this to maybe 50. So that means I'm asking GROMACS to save coordinates every 50 steps. NSTV out, that is the same thing, save velocities. In this case, it's velocities. Energies means GROMACS saves a separate file for that contains energy information of the system for every step. So I'll save it every 50 steps, and NST log 50, update log file every 50 steps. So these are the set of parameters on how the GROMACS imposes constraints. There's a method called links. That means, so what links algorithm does is, if let's say you have a set of 3 atoms that form 2 bonds. So if so these 3 atoms will have a bond angle. So there are certain amount of permissible values for this bond angle. That means these set of 3 atoms can have only a particular set of bond angles. If they deviate too much from that values, then links algorithm will give you an error saying that there's something abnormal with the system. So if you get links error, that means there's something abnormal. So that's the basic explanation of what links algorithm is. Then non-bonded settings, these are parameters that describe how GROMACS measures non-bonded interactions, that is hydrophobic as well as electrostatic interactions. The electrostatics paragraph shows what method GROMACS uses for measuring electrostatics. These are two advanced concepts, so I won't be going deep into the details. And then here temperature coupling is on. So when I mentioned the ideal gas equation, where we fluctuate pressure so that temperature is we get temperature accordingly. So this is a method called V rescale, how we adjust the temperature for the system. And pressure coupling is off. That means we are not maintaining constant pressure here. PBC equals XYZ means we are imposing normal PBC. That's all. So velocity generation here, that it shows. So when we say gen's velocity generation, so here we say gen velocity equals yes. That means we are telling GROMACS generate velocities. That means impose velocities on the system. Then generate temperature is a random. This is the system imposes velocities according to the system temperature. That is, we are making sure that the temperature of the system is 300 Kelvin. That means 300 Kelvin is roughly, I think, about 28 degrees Celsius, which is roughly the ideal gas temperature. And Gen C equals -1. That means, so this is a random number. So based on this random number, Gromax will impose the initial velocities. So if you want to produce variations of the same simulation, you can choose, you can change this number. You can give any number, let's say 34, something like that, and and the Gromax will impose velocities according to that number. So let's say if you give -1, that means you are telling Gromax choose any random number as initial velocity seed. That is, uh, assign velocities based on any random number. So that's how the Gromax imposes velocities. So uh, these are all the this is all the explanation of what is present in a equilibration MDP file. So I'll just close this here. So we will give this command now, gmx space grow mpp dash f nbt.dp dash p topol top dash c em dot grow dash r em dot grow. So the reason why we are giving dash rem dot grow is, so from the when I showed you the position restraint file, it's showing all the atom numbers. So it needs a reference structure from which it needs to take the positions. So this dash rem dot grow is the reference structure from which the Gromax imposes position restraints on the protein. And dash o nvt dot tpr. Okay, so we will give the command now. Okay, so the Gromax has done the grow mpp command. So now we will run the actual equilibration. So for that, we will give the command gmx space mdrun dash defnm nvt dash v. So we'll give this command gmx space mdrun dash defnm. Defnm means uh, I'm telling Gromax to give all the output files as nvt dot dash. That means Gromax generates whenever it does a simulation. Whenever Gromax performs a simulation, it generates 3 to 4 kinds of output files. I've explained what are those. So when I say defnm nvt, it will give the name of all the output files as nvt. So, and I'll press dash v. Dash v means Gromax will give all the extra information. So if I don't give dash v, it won't give the extra information related to simulation. So I'll give the command now, and it's running.
Rajas,
So yeah.
there is a question like what is NVT and NPT? Like someone is asking what is the basic difference between NVT, NPT,
So,
and can you define?
so I've explained the previous slide. NVT means we are maintaining constant number of particles, constant volume, and we will try to maintain the temperature constant, but we'll make sure that we will fluctuate the pressure in. We are not maintaining the pressure constant in NVT. That's the major difference. We are fluctuating pressure so that the temperature of the water and ion particles will be is brought to the temperature we are saying. So in this case, we are asking Gromax to bring it to temperature of about which is about 300 Kelvin. 300 Kelvin means about 28 degrees Celsius. So we are in the NVT equilibration. We are fluctuating pressure so that the temperature of surrounding particles will be similar to that of protein. In NPT, we will make sure that pressure is also maintained constant. Both pressure as well as temperature is maintained constant. That's the major difference between NVT and NPT equilibration steps. So I hope that's clear. So now we can see that the NVT equilibration is complete. So like every time we will check the grow file as well using VMD program just to make sure that there's nothing completely crazy with our system. So we can see that it looks normal. Okay. So we'll go back here. Now we will now we are done with the NVT step. After NVT step, we will perform NPT step.
So
So
Rajas,
for N, yeah.
how does like you viewed the structure and you said it looks normal. So what
Yeah.
will be in abnormal condition? How it look like? Like
So
the
sometimes in abnormal condition, the uh, some uh, for in some cases you can, yeah, some atoms, you might see that the protein will be displaced too much. So in this case, when I showed you when I observed the protein, we can see that the protein is in the center of the simulation box. Sometimes the protein might be displaced too much. That means something abnormal is happening. In some cases, one part of the protein will be uh, stretched too much
check.
with respect to the other. So these kind of things might happen. So in some cases, some water molecules might be too close to protein. So in those cases, it's very difficult to just tell by looking from VMD. But in those cases, GROMACS itself will give you an error.
Okay.
So these are one of the few ways to check. So there's one more question. If there's any way to, uh, maybe I'll just.
Yeah.
Can
The
you repeat
question
the
is,
question, please?
yeah. Is there any way to check this NVT NPT equilibration step is working fine? I mean, like other than viewing structure manually.
Okay. So one way you can check is there will be something called as log file. So in every step, GROMACS prints a log. So this log file is basically a text file. You can open using any text editor. You can there GROMACS prints all the information regarding with respect to this particular simulation, that particular step. So there you can check essential parameters like, so I'll open vi-nvt.log. I'll open the nvt log file. So you can see all the starting parameters that GROMACS is using. These are all the extra information. So it might be sometimes it might be very useful for us, and GROMACS prints all those information in this file. So here it shows the information for every step. Step 0, these are all the energies. You can check the potential energy, most importantly. So you can see the potential energy is minus 5.9 into 10 to the power of 5 kilojoule per mole. So since it's minus 5, it's at minus 5 into 10 to the power of 5. That means the system is pretty stable. Uh, in the same way, it prints for every 50 steps. You can check it. You can check the final value as well. So this is the final step. You can check the final potential energy. It's minus 5.3 into 10 power of 5. That means the potential energy is maintained more or less constant. That means it's somewhat uh, the system is quite stable. In the same way, we can also check temperature. Here it's showing the temperature. So it's showing 3 into 10 to the power of 2. That means the temperature is 300 Kelvin for the first step. We can check, so you can see that temperature is varying here because the pressure is fluctuating, the temperature also fluctuates. So but ultimately it comes on to the range of 295 to 300 Kelvin. You can see here. Here the temperature is 296 Kelvin, and at the end temperature is about 279 Kelvin. But at the end the temperature will be maintained to, because the problem here is we have performed NBT step for a very short time, just for the sake of simulation. So if we perform a longer set of NBT equilibration for about 50,000 steps, at the end of simulation, normally the temperature will come to about 300 Kelvin. So that's one way to check, make sure that the system is normal.
Can we see this like graphically? Someone has asked like
Yeah, you
XVG
can
graph
see
or
this
something.
graphically as well. So check this graphically, there's a Gromax tool called GMX Energy. So I'll type GMX space energy. I think -F is nbt.edr. So remember I told you EDR has all the detailed information regarding energy of the system. So I'll use this as the input, output temperature temp-nvt.xvg. So I can give this output as a graph for xmgrace file, xvg file. So here the GMX energy is asking what exactly do you want me to calculate? Do you want me to plot? So there are different parameters, bond, angle, proper diagonal, and so on. There must be temperature somewhere. Yeah, 16. Number 16 is temperature, so we'll give number 16. And it says end your selection with an empty line of 0. So I'll give 0. Yeah, calculated now. So we can check this graph. So here's the graph. We can open this with a program called xmgrace. Uh, so it will open the file as a plot. So you can see the temperature. You can plot the temperature this way. So I hope it's clear. So I'll be explaining how to use xmgrace and how to use the Gromax analysis tools in the next session, which will be analysis. But you can use these tools to during equilibration to make sure that your system is behaving okay. There's nothing terribly wrong with your system. So I hope it's clear. So it's asked the present graph says
Yes.
is stable or not. So one way to determine if your system is stable is in terms of temperature. The we had, if you remember the parameter file, we had asked the Gromax to keep temperature at 300 Kelvin. So you can see that there are many variations in the temperature. Uh, that's because we have the equilibration we have done is too short. We have done it only 500. So it's too short to maintain temperature, too short to 500 steps. You need to do minimum 5,000 or 10,000 steps at least to make sure that the temperature becomes stable. So one good way is to make sure that one good way to make sure the system is stable is by checking the temperature, making sure that the temperature remains stable at around 300 Kelvin, which is exactly the temperature you have you had given in the parameter file. So this is one of the one of the popular ways to make sure the equilibration is performed correctly. So now that we are done with the NVT equilibration, we'll proceed with the towards the NPT step. So for to get the MDP file, you can go to this link which I have given in the presentation. You can download the MTP file from this link. So So we'll briefly check what's inside this parameter file, biNpt.mdp. So you can see that it's almost the same as the NVT equilibration file. Almost all the parameters are same. There are very few cases where the parameters are changing. Here also I'll make sure, let's say this time we'll keep it as 1000. Time step will make sure it's same. Number of steps this time will be for 1000 steps. This I'll change to 50. So you can see that all the other parameters are same. Whatever we saw in the NVT parameters, NVT parameter file, all those parameters are same. Only place where it's differing is, you can see that there are another set of parameters for pressure. If you remember, I told you I told everyone what's the difference between NVT and NPT. Main difference being in NPT we are making sure the pressure is also constant. So how are we maintaining this constant pressure? We are imposing something called as pressure coupling. That means it's a method GROMACS uses to make sure that pressure is also constant. So here we are imposing an algorithm to make sure the algorithm called Parinello-Raman to make sure that the pressure is constant in the system. This is different. This is also pressure coupling type means it's asking in what way the pressure is maintained constant. That is, when I say isotropic, that means it makes sure the pressure is constant with respect to all the directions x, y, and z. So you can see that all the other parameters are same, except you can see that gen velocity is no. That means velocity generation is off. So does that mean we are not putting any velocities on the system in this case? Answer is no. So I'll explain you what happens here. So we'll close this parameter file and we'll do this growmpp step, growmpp command. So gmx growmpp -f npt.mdp -p topol.top -c nvt.grow -p nvt.cpt. So you can see that we are adding a new parameter nvt.cpt. That means cpt checkpoint file. So after certain number of steps, GROMACS saves the information on velocities in a file called as checkpoint file. So this is basically a binary file. So this file contains information about all the checkpoints. So in the NPT step, whatever velocities were present on the protein, it was saved at the end of the NPT step. All of those velocities were saved in this nvt.cpt file. So since it's a checkpoint file, we are continuing where we left off. That means when we give t and nvt.cpt, we are continuing with the same velocities where NVT simulation had stopped. So which is why we are giving this t nvt.cpt. Then it's the same thing in our nvt.grow. Output is npt.tpr. So we'll give this command. Okay, it's done. So now we'll run the equilibration step. Gmx space md run dash npt dash v. So now it's running. So I hope everything is clear so far. If you have any more questions, you can ask now. Is anyone having any more questions for now?
Not no. If participants you have any questions, you can type your questions in chat box or use raise hand option. So far, like any doubts in these steps, any queries about any files, you can ask. There is a question,
So
Rajas.
yeah, so
How
there was.
stable graph peak looks in your point of view?
I'm not sure to have understood what is the stable point
Maybe
of
in
view.
point of energy or temperature, how it should be
Okay.
like.
Okay, so we'll just check how does it look like. We'll do the same thing what we did GMX energy for this step as well.
Yeah,
So we'll try
I completed
GMX
NVT
space.
and NPT steps. How
Yeah.
it should be stable here.
So we'll try GMX space energy dash F npt.edr output temp npt.xvg. So we'll try for temperature. So we'll check how the temperature graph is for NPT step. So you can see that if we compare with the NVT graph, that is, you can see that there is very small variations in the temperature. So most at maximum the temperature variation is about 2 to 4 degrees. If we compare this with the another with the NVT file, so So let's when we compare, so you can see two different graphs. The black one is of the NVT temperature graph, and the red one is of the NPT temperature. Sorry, the red one is the NVT temperature graph, and black one is the NPT temperature graph. So you can see how the differences are in the temperature. So you can see that in the after NVT step, in NPT step, the temperature has stabilized. So this is how usual stable graph looks like. So I hope I have cleared that question. Hello. So
Rajas.
yeah. So now we are done with this. So now that we're done with this, we move to the final step, which is the production simulations. So we have done all the simulations. So now we will do. Oops. Now we will do the actual production, actual MD simulation of a protein. So what will MDP file? So you can see that it's the same. It's exactly like NPT file. There's almost no changes. Only difference here is that if you remember in the implementation steps of NPT and NPT, we had imposed position restraints. Now we don't have any position restraints. We have removed position restraints. We have left the protein free because now that after the equilibration or non-protein atoms are similar to protein in terms of thermodynamical properties. We have removed the position restraints. So we have left the protein free, and now we are doing the actual dynamic simulations. So all the parameters are essentially the same. They mean the same thing. Here you can see that we'll be performing for we won't be performing in this lab. Find it somewhere else. But if you have comfortable in the laptop, you can definitely try that. So we'll be trying a simulation of 10 nanoseconds, and basically the parameters are essentially the same. That means the set of parameters you will see from the between the NPT and NBT step, between the NPT and NPT equilibration step and MD step are very much similar. So we will try the MD grow MPP step, that is GMX grow MPP f md.mpp p propol c n. So since we are not putting any restraints, we won't be giving the dash R option. That means we are not putting any restraints. So here tnpt.cpt omd.pp. So we'll give the steps and so now we'll do the MD simulation, actual MD simulation. GMX MD run def nm MD dash V. So now the MD simulation has started. So this is all, that's all in the set of preparation steps of the MD. If you are using a normal laptop, in my case, my laptop has just 4 cores and 1 GB of RAM. You can see how much time it will take to complete 10 nanoseconds. So here you can see a message. This is giving me an estimate on when it will finish. So it says will finish Thursday, May 28th, 8 o'clock. So that means it will, I'm starting this now on Sunday, it will finish on Thursday. So you can see that MD it takes a lot of computational resources. So if you have access to a cluster, or if you have maybe more powerful computer, like say 16 to 32 cores, you can definitely try that. Or you can try this. There's a website called VNMR. So it's spelled as WE space NMR. So I can just show it to you. So you can try V space VNMR space GROMAX. You can search it in Google. You'll get to a website where it shows where there's a server to do MD simulations using GROMAX. So you can try that. You can try to do your simulations using that server as well. So in our next presentation, which is next week, we will come back here and we will do the analysis on the simulations we have performed. So I think there was a question. Pranav,
There's a question.
Can you read it out?
Yeah. In POSARI ITP file, we define the penalty as 1000 in XYZ quad axis. On what basis it is 1000?
So 1000 is essentially the default accepted value. For normally for proteins, the accepted value is 1000. That's the standard value given for all the proteins. So if there's no derivation as such on what basis this value is given, but if in certain cases what happens is we'll be performing equilibration in different steps. So for different steps, we will reduce, in each step we will reduce this position restraint by different values. That is, in the first step of equilibration, keep value as 1000. In next step, we will try 750. In next, we will try 500. In next, 250, and so on. So 1000 is normally a default accepted value for any protein simulation.
And what if the protein size is much larger, then it is like same or we can even alter it.
I'm sorry,
See,
I
your
was
voice is so like breaking. Can you type the question?
okay. RMSD graph as RMS. Okay, can you read it again? It
Yeah, this
disappeared
is
in
a
that.
different question actually. I'm running MD simulation in Galaxy server. I am getting RMSD graph versus RMSD versus frames. I could not find any options to convert it to frames.
You mean converted it to time step?
Nanoseconds, yeah.
Okay. I'm not sure how the Galaxy works. Normally, if you want a crude way of doing it, you can check your MTP file. Uh, you can check what was the time step and how many steps were performed. Based on that, you can calculate how much time does each frame correspond to. So let's say if you have an idea that one frame equals 1 nanoseconds, then you can just replace those frame number values with nanosecond values. So that's one way of doing that. But normally, I'm not sure how Galaxy server works, but normally you should be able to uh, download it as nanosecond in terms of time frames as well. That depends. So if you are if you calculate RMSD from a PDB file, that is not as a from a multi-frame PDB file, then it doesn't give you the time step. It gives you only the frame number. If you use XTC file, then it will give you in most of the cases it will give you the time frames, time step.
There is another question. What if we have a large protein in size? Then could we change the number 1000 or it should be same for every protein, small or large, independent of the size?
Normally it's the same because so what you see in the position restraint file, it's for every heavy atom. You should remember we are applying this not on the protein as a whole, but we are applying it on every heavy atom of the protein. So we should look at it in that term. So for a normal heavy atom, carbon, nitrogen, and oxygen, thousand value is sufficient. So regardless of whether the protein is large or small, 1000 value is pretty much the standard value. So, is there any other questions?
Is there any other questions you can ask or you can type in the chat box? So this 1000 will like we don't have to change, right? Like it's like default.
Yeah, in most of the cases it's default, but sometimes what people do is they try to reduce the number. That is, they'll try to do 5 steps of NPT. Let's say in step number one, the value is 1000. In step number two, value is 500. Step number three, value is 250. Step number four, value is 100. Step number five, value is 0. So if your system is, let's say, little bit unusual, if your protein system is a little bit unusual, it's if you have something like a membrane protein, people sometimes do that so that you are gradually relaxing the protein. So the server name is called VNMR. I'll type. Maybe I can show it again.
Yeah, sure.
Show.
Can you show the site?
Yeah. So Okay. I don't remember the exact website, but yeah. So this is the website. You can just search VNMR space Gromax. Oops, not this one. So it's this one. So it's essentially maintained by the server is funded by European Union, and so you can submit your MD simulations. You can do your initial steps, that is equilibration and MD steps, using this server. So there are two options. But the thing is, you need to create an account with this. So you need to create an account here. For that, you need to send a request. So you need to go to the VNMR website. I think the URL is www.vnmr.eu. You can, I don't remember where do we create an account. We have to we have to submit a request to create an account. I think they will take some 2 to 3 days to process that, and they'll give you a username and password. So not sure for singles. Okay, Gromax web server is free of charge. Access is single sign-on authentication. Become a member of VMware research community. So I think it's somewhere in this website we need an account. So once we do that, we get a login ID and username ID and a password. So we'll have to use that credentials to perform the simulation. So here you can see that you can start your simulation with a file. You can specify how many nanoseconds do you want to do the simulation. This is the output resolution, that is.
I have shared in chat. I think that's the URL.
Yeah. You can choose the force field. You can choose which force field do you want to view. The solvent model as well, and all the other stuff. So you can use web portal to try your simulation. If the simulation does not run, I'll do the simulation from my side as well, and I'll be sharing the trajectory next week. So in the next week, hopefully in the same time, we'll come back and I'll be taking another presentation on how to analyze the simulations. So in the analysis part, I'm planning to cover the basic steps, that is RMSD, RMSF, and hopefully we will do some principal component analysis as well. I think these steps will be this much will be more will be quite sufficient to cover in a span of 1 to 1.5 hours.
Rajat, there is a question. So the penalty values again about that question. So will that penalty values be same for the nucleotides as well, or like the atoms will be same or similar?
Okay.
So
for nucleotide, I have no idea because I have never performed a simulation with uh, nucleic acids before. But I think you can maybe if you go to the Gromax website, I think there's a separate tutorial for how to perform simulation with nucleic acids. So there, maybe you can get more detailed information about this. So maybe you can just Google Gromax tutorials, and you'll get to the Chromax tutorials page. I'm pretty sure there must be a separate page for separate tutorials for simulation of protein with nucleic acids. So, is there any more questions?
Participants, is there is any questions? You can type or use raise hand option. Kindly give your feedback in the link provided in the Telegram channel. If there is no more questions, so we can conclude the session. We thank you, Rajas, for his time and patience in explaining the concepts to us. Thank you, Rajas.
Thank you all for joining. See you next time.
Thank you, Rajas, on behalf of LLB Bioinfo.
Yeah. Thank you again.
Pranav, don't forget to save the record file, okay, while closing it.
Okay. It's web actually. It's cloud.